Very good morning to everyone. In this lecture, EE8451 Linear Integrated Circuits and Applications. Unit-3 Applications of Operational Amplifier. Today, we are going to discuss the topic comparator. A comparator, as its name implies, the compare is a signal voltage on one input of an op amp with a known voltage called a reference voltage. On the other input, the comparator are used in circuits such as digital interfacing, schematic trigger, discriminator to voltage level detector and oscillator. Now we are move on to the non-inverting comparator. This is one type of comparator in the given the signal of non-inverting input signal. The fixed reference voltage V reference of 1 volt is applied to the negative terminal and a time varying signal voltage input voltage is applied total the positive terminal when the input voltage is less than the reference voltage. The output becomes minus saturated voltage. When the input voltage is greater than the reference voltage, the input become positive, so that the output voltage goes to positive saturation voltage. That is, the input voltage is greater than the reference voltage, so the output voltage is positive. Thus, the output voltage changes from one saturation level to another saturation level. So, these are the non-inverting comparator circuit using the operational amplifier. The diode D1 and D2 is connected in the back to back in the two input voltages, input voltage 1 and input voltage 2, and the output terminals is a load resistance connected to the output terminal and no feedback to that circuit. The reference voltage is less than or greater than, it can be depends upon the saturated inverting or non-inverting voltage. So it can be the output voltage can be changed once the saturation level of the both input voltages. Now we are move on to the circuit. The diode D1 and D2 protect the operational amplifier from damage due to the excessive input voltage. Because of this diode, the difference input voltage of the operational amplifier diode is called a clamp diode. The resistance R in series with the input voltage is used to limit the current through D1 and D2 to reduce the offset problems. A resistance of comparative resistance R is equal to R is connected between the inverting input and reference voltage. Now we see the structure of the input and waveform of output waveform of non-inverting comparator. The first structure of input and output waves is the input voltage is less than the reference voltage, so the saturation level is a negative saturation output, and the output and the secondary, the input voltage is less than the reference voltage, so the output of the saturation voltage is positive. Now we move on to the inverting comparator. The reference voltage is applied to the positive input terminal and input voltage is applied to the negative terminal. In this circuit, the reference voltage is obtained by using the 10 kilo ohm potentiometer, that from a voltage divider with DC supply voltage VCC and -1, the wiper connected to the input. As the wiper is moved towards the positive supply voltage and the reference voltage become positive. Thus, a reference voltage of desired amplitude and polarity can be obtained by simply adjusting the 10 kilo ohm potentiometer. Now we see the structure of the non-inverting comparator. So the inverting comparator, the reference voltage is equal to the output of the inverting voltage, and then the reference voltage is equal to positive saturation voltage. So this is an inverting comparator. So the diode is connected to the D1 is connected to the feedback resistance of RF, and the diode 2 is forward connection is a RT RF connected to the feedback resistance 10 kilo ohm, and the input voltage applied to the inverting stage and the output and the non-inverting stage is connected to the feedback resistance. Now the zero crossing detector, sine wave to square wave converter. One of the application of comparator is the zero crossing wave converter. The basic comparator can be used as a zero crossing detector by setting the reference voltage is set to 0. So the figure shows when what direction an input signal input across the 0 voltage. Therefore, the output voltage is driven into the negative saturation when the input passes through the 0 in positive direction. Similarly, when input voltage passes through 0 in negative direction, the output switches and saturation positively. Now we can see the structure of input and output waveform of zero crossing detector using the sine wave to square wave converter. So the sine wave signal is converted to square waveform. So the input voltage and the reference saturated output voltage is here. Now what are the drawback of zero crossing detector? In some drawback, that is in some applications the input may be slowly changing the waveform. Therefore, a low frequency signal, it will take the input voltage more than time to cross the 0 volt. Therefore, the V out may not switch quickly from one saturation voltage to the other because of the noise at the operational amplifier input terminal. The output V naught may fluctuate between the two saturated voltage V saturated minus negative saturated. Both of these problems can be covered with the use of regenerative or positive feedback that cause the output V0 to change faster than eliminate any false output transition due to noise signal at the input. The inverting comparator with the positive feedback, this is known as symmetrical. So the symmetrical circuit of output input and output waveform and the symmetrical or square circuit are shown in figure. This is a circuit convert an irregular shaped waveform to a square wave or pulse. The circuit is known as symmetrical or squaring circuit. Now next we are move on to the multivibrator. The idea of converting a periodic waveform into a rectangular output one step further by replacing the sinusoidal input with an RC timing circuit connected across the operational amplifier output. This time, instead of sinusoidal waveform being used to trigger the operational amplifier, we can use the capacitor charging voltage. So the VC is change the output stage of an operational amplifier. Here the circuit diagram of using the operational amplifier. So the inverting is connected to feedback resistance and reference voltage is connected to the load resistance of series R1 and R2, and then capacitor is connected to the input and output voltages. So the operation of this vibrator, assume that the capacitor is fully discharged and the output of the operational amplifier is saturated at the positive supply rail. The capacitor C starts to charge up from the output voltage V out through the resistance, so the R at a rate determined by the RC time constant. We know from our tutorial the above RC circuit that the capacitor want to charge up fully to the value of V out, which is the positive saturation within 5 times constant. However, as soon as the capacitor charging voltage at the operational amplifier inverting terminal is equal to or greater than the voltage at the non-inverting terminal, so the operational amplifier output voltage fraction divided between the resistance of R1 and R2. Now the output will change its the state and be driven to the opposing the negative supply rail. But the capacitor, which has been happily charging towards the positive supply rail, that is a V saturation, positive V saturation voltage. Now the negative voltage or minus saturation cross across its plates. This sudden reversal of the output voltage causes the capacitor to discharge towards the new value of output voltage at a rate of dedicated again by the RC time constant. Now we can see the operational amplifier multivibrator voltage. So here the operational amplifier inverting terminals reaches a new negative reference voltage, minus a negative reference voltage at the non-inverting terminal. The operational amplifier once again changes the state. The output is driven to opposing the supply rail voltage. So the positive voltage saturation, the capacitor now sees a positive voltage across its plate, and the charging cycle begins again. Thus, the capacitor is constantly charging and discharging, creating an stable operational amplifier multivibrator output. The periodic of the output waveform is determined by the RC time constant of two timing components at the feedback ratio established by the R1 and R2 voltage divider network, which set the reference voltage level. If the positive and negative values of amplifier saturation voltage have the same magnitude, then the T1 is equal to T2 and the expression is given. The period of oscillation becomes. Now what is the expressions? Here the expression of beta is equal to R2 divided by R1 plus R2, and the time is equal to 2 RC into 1 plus beta divided by 1 minus beta. Here the frequency is a 1 divided by time period, where R is a resistance and C is a capacitance in natural logarithmic of the feedback fraction, and the T is a periodic time in seconds, and F is also a oscillation frequency in hertz. Then we can see from the above equation that the frequency of oscillation of operational multivibrator circuit not only depends upon the RC time constant but also upon the feedback fraction. However, if we used the resistor value that gave a feedback fraction of 0.462, then the frequency of oscillation of the circuit would be equal to just 1 by 2 RC, as shown because the linear log term become equal to 1. Now we move on to the waveform generator. This is another title of application of operational amplifier. The waveform generator is an electronic circuit which generates a standard wave. So there are the two type of operational amplifier based waveform generator. Number one, square wave generator. Number two, triangular wave generator. In square wave generator, the it is an electronic circuits which generates a square wave. This section discussion about the square wave generator. The circuit of an operational amplifier based square wave generator is shown in figure. Here the circuit diagram, the resistance of R1 and R2 is connected between the inverting input terminal of the operational amplifier and the output of operational amplifier. So the resistor R1 and R1 is used in the negative feedback. Similarly, the resistor R2 and R2 is connected between the non-inverting input terminal of the op amp and its outputs. So the resistor R2 and R2 is used in the positive feedback path. The capacitor C is connected between the inverting input terminal of the op amp and ground. So the voltage across the capacitor C will be in the voltage as at the inverting terminal of op amp. Similarly, a resistor R3 and R3 is connected between the non-inverting input terminal of the op amp and ground. So the voltage across the resistor R3 and R3 will be in the input voltage at this non-inverting terminal of the operational amplifier. Now in this structure, the negative feedback, that is the resistance of R2 and R2 is connected between the non-inverting input terminal of the operational amplifier and produce the output of the sequence. So the resistance in the R2 and R2 is connected is used to positive feedback path through the voltage across of R3 and R3. So in this session we have to discuss the comparator, multivibrator and waveform generator using the operational amplifier due to the applications level. Thank you for watching this video.